separating it from a larger body like cutting, sawing, there's casting and forging, welding, brazing. All of these are important. Yeah, I want to make that point. It's not as though now AM will start and all of these will go for a toss. No. So, but these are traditional techniques. They will be there always. AM seeks to replace some of them, some of the times, right? That's important. I don't think we need to go into this. All the subtractive techniques, for example, are bottom down. You start with a huge chunk of material, and then from that you machine out in an elegant way as well as you can the kind of part that you want, right? Additive, on the other hand, everything you have heard of, layer by layer, top down, right? So you kind of use what you need. You don't create junk alongside that. Simple way of doing that, right? Let's see. I always like to see the definition. How do people define AM, right? So if you look at the International Organization of Standards, right, they define AM as follows. The process of joining materials to make parts from 3D model data, usually layer by layer, yeah, as opposed to subtractive manufacturing and other formative manufacturing technologies. Yeah, you have many categories of AM today. If you start Googling, you'll see all sorts of stuff come up, yeah, which somehow fulfills at least some parts of this definition, right? Powder bed fusion, all of us tend to accept that. Directed energy deposition, and I intentionally sequenced it in this manner, yeah. Binder jetting, material jetting, yeah, little less used. Material extrusion, yeah. I honestly, I didn't know that this is classified as AM. I didn't know that, but apparently it is. Sheet lamination, what the hell? You stack these sheets together layer by layer, so it is AM. No, I don't agree, but I must tell you what is out there, right? Vapor, this goes into a regime which I said I will of course not cover. Yeah, but be that as it may, for me, what is relevant the most from a metal additive manufacturing standpoint are these two: powder bed fusion, directed energy deposition, right? So we will spend most of our time talking about these two, right? And if something else is interesting for whatever reason, we will take it over lunch, tea, or at the guest house, yeah? So, guys who are wedded to AM always like to talk about this: wide-ranging benefits over traditional manufacturing, design freedom, reduce material wastage, shorter lead time. The reason I decided to pick these three and not go through a long list about sustainability, this and that, is because I believe in these three, right? Whether it is sustainable or not sustainable is a different issue, but these three are always true. Yeah, there is no ambiguity about the fact that if you do something by AM, it gives you immense design freedom, right? Which therefore leads to lightweighting and things like that. Yeah, there's no two ways about that. If you do something bottom up rather than top down, via machining, drilling, all that stuff, you don't produce this kind of wastage or scrap, right? No confusion about that either. And therefore it leads to shorter time. And any of the advantages that are directly related to these three, I agree with, right? I will stay away from sustainability because I relate that to design specificity. But otherwise, if you say, okay, I can print just in time, yeah, of course. I can make patient-specific implants, right? I have a Swedish colleague who is 7 feet, and I have a friend from my BTech days who's struggling to reach 5 feet. They want different hip joints or dental implants. You can make patient-specific implants, right? All of those benefits are pretty clear. So no point in arguing about that, right? Uh, you use all the tools at your uh, disposal to make it happen, right? So you have design data. This is something going on the side, but you rely on digital data. You rely on good quality feedstock, yeah, and you rely on an appropriate heat source to make metal AM happen, right? Now, we will at different points of time talk about all of these three, right? During the course of this talk. Feedstock will be part of a different lecture perhaps, but you harness the benefits from all of these three to be able to do crazy stuff like that, right? In a very convenient way. In terms of size and complexity, what can you do, what can you not do, right? I think that is controlled entirely by your imagination partly, and partly by your designing skills, right? That is what limits it. Otherwise, you can do just about anything, right? This is something that NASA does, but right in the same building where I sit or have my office, GKN Aerospace makes similar looking parts which are taller than this guy, yeah, by DED wire, right there, and they fly, yeah. So just like some people may try to sell you that, oh, AM is, if you use AM, you're sustainable. That's wrong. There are other guys who will tell you that AM is all hype, not reality. There'll be other guys who will tell you that as well, right? Even that is not reality, right? And as educated people, our job is to filter what this group is saying, filter what that group is saying, and kind of zero in on reality, right? So the reality is somewhere in between. Yeah, yes, usually it is sustainable. It's not hype, it's real. But in some cases, it may be meaningless to look at AM as an alternative production route. Yeah, and this is also important to note that all of these are realizable, yeah, using appropriate tools, right? So you can do many, many fun things at different length scales. That's important, right? Because I've heard people say, oh, AM is okay, like for only small parts. Yeah, small parts because you're looking at PBF. Maybe you have a 9-inch by 9-inch or 6-inch by 6-inch build volume and say, okay, we will do only small parts. No, these are real, they fly, so no problem. So how does a typical AM process flow look like? I'm being little generic here, but identify the part, yeah, and somewhere in between, I will say, decide if that part is appropriate to be AM built, right? First of all, right? And if it is appropriate, you identify the AM process. It could be one of several that we will talk about, yeah? Prepare a CAD file for that, yeah? Do a layer by layer slicing, so that you know how to print, then actually print and post-process, right? So we are going to talk about several aspects of this in different modules of this course, right? Incidentally, I took some of these slides from my postdoc, Ashish, very smart guy. He's in Finland right now. So we'll talk about most of these things. So at the moment, this module and the next one, we will focus more on the printing part, right? So what concepts do you need to know, yeah, to exploit AM? You need to know about the raw material. What quality of powders do you need to use? What quality of wire do you need to use? In some cases, it could be liquid, but we will not talk about that. But powders and wires especially, right? You need to better understand how melting and solidification takes place, right? In some cases, and we are not going to talk about that either, You want to see if you can take some signals from here, right, during melting and solidification, learn from those signals and do some sort of a feedback loop to be able to control how you print. Yeah, that is crucial. You want to do sometimes, depending upon the application, some mechanical post-treatment. I'm going to differentiate this little bit from some post-treatment that is inevitable to make the part, depending upon what process you use, but something that you need once the part is out to actually deploy it in real use, right? So it could be mechanical in some cases. In some cases, it could be thermal. Yeah, and we will talk a lot about this part. You also need to understand characterization of these parts. I don't know how many of you come from a metallurgy background. How many of you have seen the structure of an AM part? If you can raise your hands. Have any of you had a chance to see the structure of an AM part? You two, but that's rare. Anyone else? 3? Yeah, but very few. Most of you others have not, right? So it's important for you to be aware of how the process or the process parameters you adopt, how do they influence structure of the built part. Yeah. For some of you, it may just be curiosity. For some others, it may be something that is very important because, believe it or not, this eventually reflects what mechanical properties the part will have. Yeah, I see Dr. Manjaya nodding, so probably he does a lot of that in his research. And then after all this, you need to see whether what you have built, can it sustain a real application for a long time, right? If it cannot, does it need to be surface engineered, right, in some manner? So if you want to fully exploit AM, you need to have a fairly decent understanding of all of these things, right? Sometimes you may not, but someone else in your team might have, or you may collaborate, but the important thing is all these things are crucial, right? And I spoke about structure, the metallic structure of this. That was just one example. Someone like Dr. Manjaya is necessary with good background in materials engineering. I think the 2-3 hands that went up also are in some way associated with materials engineering. So different parts of this cycle require different kinds of expertise, right? Data science, design, yeah, robotics and automation. You need knowledge of all of these, right? Does anyone want to argue about this, right? That it is interdisciplinary or whatever. Powder metallurgy, how do you make the powder? Yeah, is what people say that it should be completely spherical, the powder particle. Is that true? Or you can manage without that? Is it a sales gimmick that powders must be absolutely spherical? It should have 0 islands, no, each particle. So if you touch all these bases, then you are more competent to answer all these crazy questions, right? If not, you can still survive, but then you have to believe in whatever someone is saying, correct? So that's important. Let's look a little bit at what the canvas looks like, canvas of additive manufacturing technologies, right? So there are essentially 2 broad categories, one associated with electron beam. Different kinds of electron beams could be laser, energy beams. One could be laser, one could be electron beam. The other, of course, is arc. People used to call it a poor cousin of the energy beam technologies, but I don't think so. Fairly proficient in, let me see if I can, this is incidentally what I'm showing you here is everything that we have in did it start or did but doesn't matter, it's not important. Yeah, but what I wanted to show while that video is going on the side is we at our university have access to all of these things that I encircle here, right? We have an electron beam equipment from GE Additive. Earlier it used to be known as RCAM. It still remains one of the very few companies that makes electron beam powder bed fusion equipment. We recently have procured a powder bed laser equipment from Aconity. Has a fairly good size build volume. We have also been working for the longest time, even before it was fashionable to call it additive manufacturing, for almost 20 years now. We have been working with direct energy deposition using wire. And this big part that I have mentioned, made by GKN Aerospace, is an outcome of some of the low TRL work that we did with direct energy deposition during wire. So we touch all of these bases. More recently, we have been beginning to pay more and more attention to VAM also. It's not as useless as people want you to believe. It's cheap, but it's very useful. And we have begun to use it to make, at least in a preliminary way, many gas turbine parts and things like that. Yeah. Have any of you seen an EBM machine anytime, anywhere? There are very few in India. There are more SLM machines, I think, in India than EBM machines. No, but I will try and run you through how this works a little bit. Yeah, so if you look at an electron beam machine, as the name suggests, it uses an electron beam as an energy source, right? And powder as feedstock in most cases, right? To 3D print any metal component. We are going to focus now on a powder bed, right? What do you think a powder bed fusion means? Just guess from the name. What is powder bed fusion? BTech. What is powder bed fusion? Yeah. But then what is bed fusion? Forget about powder. Yeah. Not too hard to convert, not too easy to break. You're MTech, guys? BTech only? With the help of UV rays. In this case, I have already said we are using an electron beam. So it's okay. Yeah, but MTech. So, next step, that's correct. So you use the powder, you make it in the form of a bed, yeah, and you use the electron beam to locally fuse in regions of interest. Those regions of interest being dictated by what your 2D slice looks like, right? So that's simple, right? So let's talk about some of the hardware issues. I actually had a full video of the RCAM equipment we have, but I couldn't accommodate it. So this is what it looks like. It's somewhat a lab type equipment for EBM. It has two essential parts. It has this electron beam column, just like you would have in an SEM, for example, if you have seen a scanning electron microscope in a very loose sense, something like that. Yeah, and then you have a processing chamber which has twin powder hoppers where you feed the powder that you will utilize to make the component. It has several other, the hardware has several other crucial components. It has a rake. What's a rake? Yeah, it will take the powder from the hopper and form a bed with that. Yeah, it will spread the powder. So that's a rake, right? And then the electron beam will locally fuse the powder, and then the rest of the powder will go away, or it will remain unsintered, not go away, I'm sorry. Then this stage, there is a, you start with a what is called a build plate, and then this will advance depending upon what your layer thickness is. Again, a new bed of powder will be raked. Again, you will locally fuse. Maybe this, now what you fuse would be a little bit different compared to the earlier layer, because again it will be governed by the slice data. So, and that's how it proceeds until you have built the part that you have designed to build, right? So, just what I said, thin layer of powder distributed and welded, every layer. Part size is limited, as I was saying, to whatever your equipment allows you to handle. You can't build the kind of cone that I showed right now in such a chamber, yeah. And eventually, whenever you stop, the whole build volume will be filled with powder, with the component kind of embedded inside, where it was sintered by the beam, right? So, or fused by the beam. I have some videos. I don't think they do justice to what actually happens, but it's a very interesting process to look at, right? One nice thing is the electron beam that moves, it moves so quickly that you can simultaneously maintain several melt pools at a given time. If you don't believe me, I hope there is some video that will show you that, right? So it's so quick that there is something molten here, here, here at the same time, because it's moved so quickly, right? And that is extremely fascinating. Here is an example where you have a rapidly melting line at different segments at a given time, right? So that works very well. And how do you move this point? Yeah, that determines structure. So on the face of it, it's very simple. At another level, it needs some significant knowledge of what will happen depending upon how you jump these little beams around, right? So, and then eventually once the process is done, the sintered powder with the build parts will look something like this, yeah? Looks like crap actually, it looks very bad, right? But once you take the unsintered powder out, once you have removed that, then you have whatever you want. This may look like a very unimaginative build, right? Not terribly exciting, but as an academic, this is very exciting, correct? Why is it exciting to do something like this? For various reasons. We are trying to build here blocks, yeah? So we are looking at different build strategies, right? So this may be built with the laser beam dancing around in a certain way. This could be built with the laser beam dancing around in some other way, right? The size is such that we can, for example, do tensile test specimens or fatigue or creep. We can fabricate them in this direction, or we can fabricate them in this direction, right? Why would we want to do that? Why do I want to build a tensile specimen like that, fabricate, and why do I want to do it like this? To study what? Strength. Yeah, I'll make tensile specimens to measure tensile strength, but yeah, that's not the answer I'm looking for. Loaded direction, correct. So go one step further, then you get 100 out of 100. Anisotropy, correct. Yeah, I'm interested in seeing if the mechanical properties are same in the build direction and the direction transverse to it. Yeah, because many of these, at least reportedly, tend to be very anisotropic in properties, right? So that's what I want. And then I also want to look at what happens if my wall thickness is thin, thick. So this kind of a build allows me to do many things, right? So this is a bread and butter build we call. If you make one build like that, it's one PhD and little bit of a postdoc, right? So one build like that keeps us busy for a long, long time. Yeah. And then, of course, it need not be like this. It could be more complex, and you can build just about anything, right? So that's important. Let's look at some other things. There's a heat shield here, right? For preheating, we have couple of, I told the rest of you. Yeah, vacuum. So this is done under vacuum. We have roughly 10 to the minus 3 millibar level of vacuum, and the nice thing is there are only two moving parts. One is the rake that comes and sweeps the powder. The other is the bottom platform that goes up and down, mostly up, yeah, depending upon what layer thickness you have, right? So, anything else? Yeah. So, then all of you know what the purpose of the rake is, to apply a thin powder layer. Now that is a process variable, mind you, right? How thin do I make it? Do I make it 30 microns? Do I make it 50 microns, 60 microns, right? So that is something I can vary, and that is one of the process variables that people usually investigate, right? And your Z direction, up and down motion, will be dictated by what powder layer thickness you choose to employ during your build, right? Let's talk a little bit about the process then, right? And there are some, hopefully, videos that fascinate you. So you always have a support structure on which you start building. What does it mean? Eventually you need to take it off. Yeah, you need to remove the support structure, right? And your geometries could be as complex as possible. There is usually no constraint, but they have to be within the build plate that your chamber can accommodate, right? So that's the main thing really. So the typical layer thickness that we have used in most of our work has been between 50 to 90 microns. Sometimes that is also dictated by your powder particle size, but that's a complicated interrelationship. But we have kind of changed it during this over this interval, and that works quite well. So if you have to define the steps involved in processing, right? So it starts in powder bed fusion with application of a layer by a rake with whatever thickness you choose. Then you use an appropriate power for your electron beam. Yeah, we usually use something of this sort, which can be varied about 3 kilowatts at fairly large speed. We can vary the spot size as well. There is a certain focus spot size for the electron beam, but you can defocus if you choose to build it with the electron beam gun little bit further away from the focal distance. Then you get a defocus spot. Sometimes you may want to do that for certain kind of applications, and then you program it to scan. So the scan strategy is important in how you make this beam jump, and then depending upon what material you are depositing, you govern the temperature that's there as well, right? Our experience with our equipment has been that you can maintain up to 40 melt pools at a given time, right? So the beam is jumping, but what is melted is not yet fully solidified, right? And that's what it means. It doesn't mean 40 beams, right? It is 40 live melt pools, yeah, which gives you some indication of how fast the thing can move. Yeah, and these are basically research interests. What is the influence of power? What is the influence of scan speed, do we do it in focus or non-focus, but just talking here about the capability of the beam, right? Now Dr. Manje has showed me the trick of how to make my videos work. So this is powder raking now, right? So then little bit of preheating and sintering, yeah, using a laser beam, and then we do a contour. We will stop there and see if you understand what contour means. So we preheat to sinter the powder, then we do contour melting, yeah, and then we do hatch melting after that. Yeah, very fascinating to see, right? Yeah, so many electron beam spots. Yeah, so this is still all contour melting, and then we do hatch melting, right? So that is hatch melting. And usually the parameters for melting the contour are different from parameters for melting the hatch. A contour is not always necessary. Yeah. So just going by English language, what is contour? Yeah, please. No, it's actually taken by a camera. Yeah, it's real. No digital.
Digital image coordination
For what?
when inside test is happening, how much strain hardening we are capturing by using a live cam like that we have done?
Yeah, so this is just a live camera. Yeah, so does that answer your question? I'm not clear about your question.
Means, what kind of camera we have?
Oh, I will have to get you those specifications. I don't off the top of my head know what camera, but yeah, it's an IR camera. It's a pretty fancy camera as well. But if you want more details, you have my email. Write to me. I'll get you those details. Yeah. So coming back to my question, what do you understand by contour? Exactly, right? So it's not mandatory, but we usually like to do the outer periphery of the part first, yeah, and then do everything inside that boundary, which is called the hatch. Usually the parameters that we deploy are different for the contour and for the hatch, but yeah, we see that works quite well. I'm not going to go full screen because I don't want to go back and forth. Yeah. So at the end of this, imagine that I have raked, pre-sintered, done the contour, done the hatch, one layer over, right? Then I repeat that. New raking of the powder layer, same steps follow. Once everything is done, yeah, as per your CAD drawing that you have kind of transported to this equipment, what you eventually get is a sintered block of powder, right? Embedded in this powder bed, yeah, a sintered part, right? The sintered powder is subsequently removed by grid blasting. The rest of the powder is just, it can be recycled, right? We will come to that in a minute about recycling of the powder, but yes, please. It depends little bit. Again, that too is a parameter of control. Yeah, but you're right. It is not required every single time because the bed is already hot. That's your question, right? The bed is already hot, and depending upon what you're building, if we do Inconel, sometimes the bed stays at 1000 degrees for the entire duration of the bed. So it is pretty hot, and that's a good point though. So we don't always use it. You can use it if you want. As with everything else, it's a parameter that you can play with. Yeah. Bed is heated. Yeah. Yeah, that's what I'm saying. It's little bit up to, it's one of the parameters you can choose to heat or you can choose not to heat. Depending upon at what temperature you are maintaining the build and whether or not you think preheating is necessary and helpful. Yeah. So, if you just finish printing, what you see is very unattractive. You know, it looks like this, pretty horrible. Yeah, but it's not so difficult. You then just use a grid blasting uh, machine. Take the rest of the unsintered powder or loosely sintered powder off. Yeah. What we do many times is use the same powder for blasting as we are using for the build, right? So that there is no contamination. So we do that sometimes, right? This is exactly what you had seen earlier. But if you saw it right after building, it looks horrible, right? So rest of the powder. What are your thoughts on what happens to the rest of the powder? Reused forever. How long? 2 or 3 times. Why not 4th time? Overheating melts the powder. Okay. Oh, but then you can't use even second time. If you're saying it forms a solid piece, you can't. For any question, you ask me anything, I'll say it depends. Yeah, and you're usually right. 90% of the time you're right. Yeah. So in this case also you are right. It depends. Yeah. But jokes apart, uh, some of the powder can fuse together a little bit, so it could be coarser. So depending upon who is using this, some people choose to sieve it, yeah, and remove the coarse uh, kind of aggregated particles, because otherwise it's not good for the properties of the build. The other disadvantage over time is something that I am looking for you to answer, any one of you, UG, PG faculty. Yeah, so size I sieve every time, right? So I get the same powder particle size every time. Yeah, there's little bit of oxidation. Yeah, every time you use the powder, there's little bit of oxidation. Again, it depends. Yeah, it depends upon what powder, but there is little bit of oxidation. Uh, you also made a good point. If you are holding the bed at temperature for a long time, depending upon how complex or how big the build is, then this powder is being heated for the same duration of time. Yeah, so that has problems as well. Apart from oxidation, you could again depends on the chemistry of the material, but you could begin to see some precipitation. Yeah, like carbides and all. So lot of things happen. So different users have different protocols. Some of them just blindly change it every 3 times or every 5 times, but almost all of them replenish. They decide how much virgin powder and how much used powder should go in each build, right? So, but this one, yes. Yeah. But 10 to the minus 3 is still, yeah. Yeah. And the other, if you are talking about nickel-based superalloys, some precipitation is also important. How do you cool it off? Cool it down. We usually let it happen in the furnace itself. Yeah. So we don't do so much to it. We let it just go on there. Yeah. Cool it, come back next day. Yeah. And do that. Yeah. So there is a, yeah. but sometimes we kind of purge it with argon. I mean, there are different ways, and 10 to the minus 3 is not such huge vacuum, yeah, in a sense, right? But sometimes we purge argon, and yeah, good point. Yeah, I'm honestly not going to talk about post processing so much here, right? In the sense that I will cover in the other module. But here by post processing, I largely mean how do you remove it from the base plate, right? So to that extent, post processing. So you can, depending upon how you have built the initial layers, you can just yank it off from the base plate. Many times you have to actually cut. If you are doing nickel-based superalloys, we many times EDM wire cut from the base plate, right, and remove whatever support structures there are. These other two parts will be a part of the other module, right, that we will talk about. If you look, we spoke about the structure a little while ago, structure of the part. The surface would look something like this, right, depending upon, yeah, how you have built that. I'm not suggesting that this is the best or the worst surface morphology, but it could look a little bit like that. Yeah, where you see islands which are fully molten, some that are not, but will melt the first time you do the next one. Yeah. So if you have to summarize, EBF, EBM is slightly a hotter process compared to SLM, right? It has low oxygen content in the chamber. The prominent steps are raking, preheating or sintering, contour, hatch, and then remove the build plate and kind of blast it off. Yeah, you even 18 tomorrow doing CM247 and then hashed alloy, and then suddenly someone says, thoda steel SS316 kar do, that's very hard, right? Because you need to clean the whole chamber, and when we are working with gas turbine especially, they don't like us to touch other materials. So if we start Inconel, we stay with Inconel for a long time. If we move to Tie 64 or something, we stay with that for a long time. Yeah. So, but that is a style in which our group works. It's not a limitation of the equipment. That's important to know, because if you scan the literature, you will see just about everything done by EBM. So there's nothing limiting. People have also done tungsten now, and just like the Aconity machine that I will talk about when it comes to SLM, even for the EBM, there are now some experimental small systems ideal for academia that are coming up, where you don't need so much powder. It's easy to move from one material to another. There's a company called Freemelt in Sweden. They are essentially guys who were with Arcam or now GE Additive earlier, but they broke off and started that. But that's, if you're thinking of buying, it could be something to consider. You don't need so much. Freemelt. The name of the company is Freemelt. Yeah? Yes, please. Maybe because there's not so much work done on that. Yeah. Again, people should see value in it, right? I mean, I don't think it's a fact that you can't do it, right? But you raise a good point. I have also not seen so much work on aluminium. I see some in SLM because that's a colder process. So maybe people, by and large, people still prefer SLM. I don't know, but we bought our EBM first, so we worked a lot on EBM. But there are far more laser powder bed fusion installations worldwide, many more than EBM. But coming back to your question, I don't believe there is a limitation, but I'm not so sure. Yeah. The electron beam in this case, yeah. No, it won't. It's essentially uh, because the heat input is localized. Yeah, and that's true for a laser as well. The heat input is very localized. So maybe I have that cartoon when I talk about SLM. So if you're talking about let's say location, it jumps 1, 15, 30, 45, then comes back and do 2, 16, 31. So uh, they are not doing adjacent to each other, right? So if you do it at one spot, the the rest of it kind of serves as a heat sink, right, in the vicinity of that. So, and and in any case, you don't care if it heats, right? But it doesn't so much. But in this case, the bed itself is pretty hot. Yeah, it stays hot. It's just the strategy of how you melt, and that, how do I say it? I don't want to jump the gun, but how you melt then will determine whether you are going to get a columnar structure or an equiax structure. Yeah, so I don't want to get into that kind of depth, right? But that is what it will affect. Yeah, and that is why you need to play around with what is called the scan strategy. It's not as though that's the only way it will do. You can do it in a completely different way. You can do all tracks next to each other, no problem. It can be done, but it's your homework as a designer to decide how to do this, right? Yeah. So some added benefits of EBM as opposed to generic AM benefits. Yeah. I mentioned that you process it under vacuum and therefore good for materials that are thermally sensitive like titanium. Titanium doesn't like any amount of oxygen. The beam speeds are pretty high, can go up to 8,000 meters per second. Since this stays very hot, you rarely require any stress relieving heat treatment at the end of the build, yeah, because there are no large temperature gradients between the layers, so that works pretty well. And yeah, it's more forgiving to inherent material properties like absorptivity and stuff like that that are important in case of a laser, right? What else? Yeah, this I didn't cover. Yeah, you need the material mostly to be electrically conductive. Your roughness is huge, and I will come back to that when we talk about post treatment. Compared to SLM or even DED, the roughness is much higher in case of EBM. This not strictly a limitation, but it is because it is done in vacuum. There is a limitation to what chamber size exists. So when I prepared this slide, this was just about the biggest EBM that was available, right? And then also, as I mentioned, not so many manufacturers of EBM equipment worldwide, unlike the laser part, right? So I knew of Arcam, I know of Fremelt, and both of those are in Sweden right now. I don't really want to go through all this. I think I could stop and we could chat a little bit, because all this you will see anywhere in literature. There are many things you can do with EBM. All difficult kind of materials. We were talking about implants. You can do different kinds of implants, very complex titanium aluminide blades, and there's several parts here as well where GKN Aerospace is looking at deploying AM, but yeah. Yeah, there are many. I just don't want to go through that unless you have a specific question. But so we're close to 1 o'clock. I guess time to stop. But we can take some questions if you have, or we. EBM works very well. Our build size is a little bit small. SLM works well. Since this was one of the first EBM machines we got, we can't do anything inside the machine. Otherwise, the guy will say no warranty from tomorrow, right? So we are worried about those kind of things. When we got the Aconity, we learned from what constrained us with the EBM. So we said we want the freedom, so we are able to now put pyrometers, etc., inside our machine, do little bit of monitoring and diagnostics. So with DED, of course, we have all sorts of freedom, right? So
My doubt is the laser travels in different multiple points. So it has some delay time to solidify. Means the laser will stop and follow to another, or just it travels from one side.
once more, please.
The laser travels in multiple points, na, sir.
Yes.
So for multiple points, the laser will
Ma-
stop
The,
at a
the,
point.
the,
or
the
just
answer could be different. You are saying laser, we are talking
yeah.
electron beam so far. Yeah.
the beam stops and just points to another, or just it travels.
You saw the scan speed, right? Almost 8,000 meters per second, travels like crazy. So there's no question of stops, right? It's more like bounces from one spot to another, right? And whether you want it to bounce or not, how much do you want it to bounce? Yeah, how far do you want it to go is dictated by the scan strategy, right? Maybe I show the scan pattern when we do VAM or laser, so you can do scan pattern, you can go there, come back, start here again. No, people use all sorts of stuff, yeah. And if you ask why, you will not get a good answer, yeah, because that depends really on how much they have investigated the effect of scan strategy, yeah. So either they may have an answer, or they just may not. Yeah, it depends. Yeah, it depends. Yeah. But for our part, we have seen that it makes a columnar structure fully equiax depending upon how we scan it. Yeah, which is completely different, and therefore it will give you different mechanical properties. So, did I answer your question? Not so okay. Yeah.
One more question.
Yeah, I have all the time. No problem.
If we point at one point, does the separate different powder materials will not stick, sir? Because due to that much heat. At a certain point, it will be solidified, but the heat will dissipate it, no, sir. Different powder will not attach.
Like a magnet.
Ah.
So it will locally sinter, right? That's the purpose also. It will locally sinter based on the CAD drawing that you have sent. Yeah. So if you are building this, for example, it's a bad example, but imagine this is what you are building, right? So you will do a hatch which is like that. Yeah. First, sorry, you will do a contour that is like that, and then you will do the hatch. Yeah. So I don't know if I'm answering your question correctly. Then I go to the next layer. Let's say I've done that for this part, then the shape is a little bit different as I rise up. Then it will do a separate part where it will sinter the new layer to the already sintered layer below, right? And the rest of the powder will be loose. That's why it looks so crappy, ugly in the end, right? And then when you grid blast, everywhere where your electron beam has not traveled, that will be removed, right? And the rest will be there. Yeah, but I think it could still, the immediately adjoining powder could still stick. And maybe that's why you get very high roughness in your EBM compared to laser. So, it depends on so many things, to be honest, yeah, including the quality of your powder. So, yeah, please.
What's the possibility of in situ manufacturing using EBM?
In situ in the sense?
I mean, like a composite silicon, just like a inoculants, adding the inoculants with the matrix.
Yeah, yeah.
Will it be possible in EBM?
In principle, everything is possible, right? But you then for simplicity and argument's sake, let's say you want to do something with aluminum silicon carbide composite. Yeah, are you thinking of something like that? Or in a sense, titanium aluminide, of course, single phase, but you're talking about two different powders, right? Yeah, correct. So nothing stops you from doing that. But the challenge for you is uh, what is good to melt element A or component A, is it good enough to melt component B, right? And when you rake it, is there any segregation because of density difference and things like that? So as you get complex with, just as with material, when you get complex with chemistry also, these issues you need to resolve. The, at the end of the day, this damn thing is a source of high energy, that's all. Yeah? How do you deal with the rest is your problem, right? But I have identical issues. Let's say I'm making a composite. I want to add hexagonal boron nitride to my wear resistant coating. Yeah? I introduce both, right? Do I get perfect homogeneity? Perhaps not. But is that slight heterogeneity acceptable? Depends on application. So at the end of the day, you always come to it depends. Yeah. So, but it can be done. The processes themselves are not limiting. So if you have two, imagine you have two constituents with very different melting points, right? You could be looking at two very different situations, right? You could be looking at one situation where my second component, I am okay if it is not molten and I get a distributed solid second phase, right? Then there is a certain way for me to try and fix process conditions. There could be another where you don't want a particulate second phase, yeah? You want to melt both of them, right? Then I will use conditions that are appropriate for the higher melting constituent, correct? And assume that the lower melting will automatically melt because I have kind of fixed my parameters for higher melting.
Negatively affects the heat input for the lower melting.
Life is not easy, boss. Yeah, you have to live with certain things. Yeah. Well, I think apart from examples, I didn't have so much to talk about. But thanks for your patience. You have survived me for more than 2 hours. Yeah. So good start. Thank you very much.